Alright, today I'm going to go over one of the most important principles for physics C, E, and M, that is Gauss's law. So, what does Gauss's law say? Well, mathematically it says the surface integral of E dot dA is equal to the charge enclosed divided by epsilon naught. So, to get an idea of what this means, first of all, whenever you use Gauss's law, you need to have what's called a Gaussian surface, which is just a fancy way of saying something that encloses a volume. Let me draw this not dashed, actually. So for a nice, easy to draw example, I'm going to use a cube. So here we have a cube, which does in fact enclose a volume. And now on this cube, we can have a little patch of area, that is our dA. Let's say it's over here. There's our little dA. And just for the sake of convention, and because we need it to be a vector, we decide that dA always points outwards, perpendicular to the surface. So I guess the way I've drawn it would actually be more like this direction, dA. Alright, points outwards. And its magnitude is proportional to the size of that patch of area. But that's not really all that important. So this expression here, E dot dA, if you remember, the dot product is kind of measuring how parallel two things are. So what we're really doing is we're looking at how much does the E field point outwards at the boundary of our cube. And since we're doing an integral across this entire surface, we're saying when you add up all the E field around the surface of this cube, how much does it point outwards? How much does the E field flow outwards of this cube? And Gauss's law says that outflow of E field is equal to the amount of charge enclosed within the surface. So let's say there's just a little charge inside the cube, divided by epsilon naught, which is just a universal constant. So what Gauss's law effectively does is it lets us figure out what's happening with the E field in some otherwise complicated or difficult situations. Let's start with the most simple situation. If we just have a charged conducting sphere with some charge plus q on it, let's say we want to find the E field at some random point out here, which happens to be a radius r away from the center. Gauss's law says we just need to draw ourselves a Gaussian surface. So this is a sphere, because remember we have to enclose a volume. So even though this looks like a circle, this is in fact a sphere. And we write our Gauss's law equation. The surface integral of E dot dA is equal to q enclosed over epsilon naught. In this case, I'm just going to replace that with big Q over epsilon naught, because our q enclosed is just that big Q. Now, we need to simplify this expression into something a bit more usable. So first of all, let's try and get rid of that dot product. Remember, the dot product is looking at how parallel two things are. And in this situation, because we know the entire thing is spherically symmetric, we know that the E field must be pointing directly outwards or inwards of the sphere at every point on the surface. In other words, we can simplify this dot product down into simply E times dA. More formally, it'd be the magnitude of these two, but this works fine. We're not sweating the details here. Then we need to pull E out of this integral, or otherwise integrate it. But in this case, again, because this situation is spherically symmetrical, we know that the E field must be constant at every point along the sphere, so we can just pull it out since it is a constant, and we end up with this integral, which we can do because we know the sum of the area across the entire surface is just the surface area of the sphere, which is 4 pi r squared. Now we can just algebraically manipulate this little equation to find that the E field at this point is equal to q over 4 pi r squared epsilon naught. And this is a perfectly valid equation, but you might be more familiar with it in another form, which is just E is equal to kq over r squared, since k is equal to 1 over 4 pi epsilon naught. But in any case, with that, you've basically successfully derived the E field around a charged sphere just using Gauss's law. Of course, that's just the simplest situation, and you probably know the formula for that. But if we combine Gauss's law with another property of electrostatics, we can take this a lot further. And that is that the E field within a conductor must be zero under electrostatic conditions. To understand what that means, first of all, electrostatic conditions just means when all the charges have stopped moving around. Let's just say none of the charges are currently moving. So let's take an example. We have a charged sphere. And let's say hypothetically, the E field here was non-zero, it was pointing towards the center. Well, then as soon as you press the play button, as soon as you let time pass, this positive charge down here is going to scooch on up into the center. And then your E field is also going to change. So then now everything's moving around. It's just a whole mess. Most of the time in Physics C, when you're asked to think about charge distributions or E fields, you're going to have electrostatic conditions, which is to say that none of the charges are moving around, which naturally means there must be no force on them, which means no E field, at least when you're inside a conductor, since with insulators, charges aren't free to move, so you could technically have an E field. So when you combine this property, that is that E field is zero within an electrostatic conductor, you combine this with Gauss's law, you can do some cool things. So let's take the classic example of a coaxial cable, which is just two concentric charged cylinders. You can also do this with two spherical shells, two nested spherical shells. But I'm just going to do the cylindrical case for some variety. So you have this cylinder stretching off. For the purposes of this example, we have to assume that the cylinder is very long, that it's infinitely long. But at any rate, so we have this inner conducting surface here. Let's say there is a total charge of plus Q on the inner surface. So I'll draw the charge distribution, which is going to be spread out all on the surface. And then on the outer conducting cylinder, we're told there is a charge distribution of negative 4Q. Well, first of all, what does the charge distribution actually look like? We don't know where the 4Q is throughout this shell. By the way, just for clarity, this entire in-between space is just non-conductor. It's air or some oil or something like that. So Gauss's law can already help us out because if we draw a Gaussian surface, here, I'll draw it in purple so I don't have to do a dotted line. If I draw a Gaussian surface straight through the middle of this cylinder, so this is still a cylinder itself, of course, because it has to enclose some volume. This is a finite cylinder. We know that the E field all along the boundary of the cylinder must be zero because the boundary is smack in the middle of a conductor. So just this statement right here, the E field must be zero within an electrostatic conductor. So the E field must be zero. Therefore, if we look at Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. If this is zero, well, then that must be zero too. So we know that there is a net charge of zero enclosed within this purple cylinder I drew, and there's already a plus Q inside, so there must be a minus Q to balance it out. So we know that on the inner surface of this outer sphere there is exactly minus 1Q worth of charge. And since we know that the total charge on this outer surface is minus 4Q, we know there must be another minus 3Q on this outer surface, so that the total comes out to 4. I didn't draw that quite right. That's only 2. So when you draw charge distributions on the exam, you do want to be roughly correct with the relative amount of the pluses and minuses you draw wherever. All right. So with that, we have our charge distribution drawn. Now let's take a look at what is a pretty common formula for an FRQ question. What is the, so I guess first of all, let me label some radii. So this is radius A, that's radius B, and then finally we have radius C. So a pretty common FRQ question is going to ask you, what is the E field when the radius is lesser than A? What is the E field when the radius is between A and B? And what is the radius, or what is the E field between radius B and C? And then what is the E field outside of radius C? So let's start with the first case, when the radius is less than A. So we need a Gaussian surface. It's just going to be a cylinder at some radius r that is within this first radius A. So it's some finite cylinder with length L. And we write our Gauss's law. Integral E dot dA is equal to Q enclosed over epsilon naught. So, alright, so with a cylindrical Gaussian surface in a situation like this, we have to do a little bit of hand waving. As I say, we have these end caps. So if you have a cylinder, right, there is the round face, right, this round face, but there's also this top face and this bottom face, the flat faces. The round face we deal with in the same way as the spherical Gaussian surface. We know that the situation is spherically symmetrical, so therefore the E field must be pointing directly out or directly in here, so we can wave away the dot product. But then what about the end caps? Well, in this case, since we're assuming that this cable is infinitely long, or effectively infinitely long, we know that the cable basically is symmetric about both of these faces, so the E field must be zero, because it just wouldn't make sense for there to be any E field pointing out this way, because as far as the cable is concerned, this is just some random point in the middle. Why should there be E field pointing down one direction instead of the other? So the E field on either surface pointing, or either cap of the cylinder pointing out or in, is zero. And then from there, we can do a similar simplification to what we did above. The dot product goes away because the E field is pointing directly out of the cylinder. And then the E comes out because we know it will be symmetrical at any point on the cylinder. And then from there, we can just pull out the surface area of the cylinder. Take note, this surface area is not including the end caps because by our previous logic, the end caps aren't contributing anything to this E field integral here. So just the round surface of the cylinder is 2 pi r L times E is equal to Q enclosed over epsilon naught. So now, I guess technically for this part of the cylinder, for r is less than A, we didn't actually have to do all this whole process, because what happens is you look at the picture, you notice that, I drew it slightly bad, I shouldn't have put the plus Q there, I'll move it, but you notice that, in fact, there is no Q enclosed, since all of the charge on that inner cylinder is concentrated on the outer edge, like a skin. This Q enclosed is just zero, which means you do some shuffling around, E is equal to zero. There you are. Now let's move on to the next case, which will be for A is less than R is less than B. So now we have a new surface. This doesn't get too cluttered. We have a new surface. Oh, that's a bad circle. A new surface. We'll use the same length L. And now we're at some new radius, which we'll also call R. Alright, so now at this new surface, I'll just mark this little green star so you can remember, or you can see which surface it matches up with. It's the purple surface. So you write out your Gauss's law, integral of E dot dA is equal to Q enclosed over epsilon naught. You do the same process as before. So you know it's a cylinder, the end caps don't contribute anything, it's cylindrically symmetrical, so you end up with 2 pi r L E is equal to Q enclosed over epsilon naught. This time our Q enclosed is not zero because we've enclosed that plus Q on that inner cylinder. So if we do some reshuffling and sub in plus Q for Q enclosed, we find E is equal to Q over 2 pi r L epsilon naught. Let's see, have I done that right? No, not quite. So, a little mistake I made. So we can't say that there's plus Q charge on the cylinder because this is an infinitely long cylinder, so we have to instead express this in terms of charge density. That's not the right. That's not the right thing to say. No, that is right. Yes, plus lambda and minus 4 lambda linear charge density, which is to say per unit length of this cylinder, there is that much charge on it. So in that case, when we substitute in for Q enclosed, we find the actual charge would be lambda times L. So we have lambda times L. The L's cancel out. And there we go. There we get the correct expression, lambda over 2 pi r epsilon naught. Okay, and now the next case, b is less than r is less than c. This is for the inside of this outer cylinder here. I'm running out of, I did not want to get rid of that, but I'm running out of colors. Let me just pull out a new one, light blue. That will do. So that's quite large. More, please. Alright, so we draw our Gaussian surface splitting the middle of this outer cylinder. Use the same length, L. And now for this Gaussian surface, we draw our, or write our Gauss's law rather. Integral of E dot dA. You should try to remember your vector signs when you're writing this, so you have that mental reminder that you need to do the little mental gymnastics to convince yourself that you can in fact get rid of this dot product, because otherwise Gauss's law is technically a dot product that you can't just do with normal algebra. But in any case, for the cylinder we do the same simplification again. 2 pi r L E is equal to Q enclosed over epsilon naught. This time our Q enclosed once again is 0 because remember we have minus 1 lambda on the interface of this outer cylinder plus 1 lambda on the interface, or on the inner cylinder, so that adds up to 0 Q enclosed. E is equal to 0. And then finally, the outer case, C is less than R. We have a big one. Let me just find a new color, light green. I think I already used that. Dark green. Alright, so out here, all the way outside of everything, we have one more cylinder. Same length, L. We draw our Gauss's law. Integral E dot dA is equal to Q enclosed over epsilon naught. Same simplification, 2 pi r L E is equal to Q enclosed over epsilon naught. This time, what is our Q enclosed? It's the sum of plus 4 lambda and minus 4 lambda, so negative 3 lambda. So we substitute that in, negative 3 lambda times L, since we need to convert the charge density into actual charge. Then we just do some rearranging, 2 pi r L epsilon naught, L's cancel, and we find negative 3 lambda over 2 pi r epsilon naught. So then, of course, on the actual AP exam, you will, on a problem like this, you would more than likely be asked to graph E with respect to R. So when you do that, let's see, this is E, this is R. They would mark for you A, B, C, and what do? Well, first of all, recognize that these expressions, I mean, these ones are obviously 0, but then these expressions are both of the form 1 over r, just with a bunch of constants slapped on. So what you do is, first of all, you draw your dotted lines here. I think these might come pre-drawn for you, but if they don't, you should draw them. And then, up until a, it's 0. Then between a and b, you have this 1 over r relationship. So like so. Then, I'll draw it a bit higher. And then, what I find convenient to do is you just continue it on as if it were going on forever. And then you leave it there for a second as a guide, because it's 0 between B and C. But then after C, Oh, I suppose this actually needs to go down. You know that this is just the same thing as this, but times -3. So at this dotted line of C, you just kind of eyeball down 3 times, somewhere around here, and then you continue from there. Just draw these dotted lines, and you draw your 1 over r relationship. And then you can go back and erase this excess over here, like so. Oop, a little bit too much. And then on the test, you just want to make sure that you can tell that it is in fact 0 in those spaces. And there you go. That would be your graph of V versus R using Gauss's law. So with that, you should be pretty well prepared to use Gauss's law in most situations. I guess, actually, I will do one more example. That is for a capacitor, which is relatively straightforward, but that is another situation that can come up. So when you have a capacitor, that's a parallel plate capacitor specifically. I want to draw that thicker. So let's say you have, with a capacitor, you have 2 parallel plates. Actually, I'm not going to draw the ends. This is an infinite plate, and then there's your other infinite plate down there. So this being a capacitor, we expect there to be plus Q here, minus Q here. So with the capacitor, all the charge ends up concentrated on the inner sides. And then from there, if we want to find the E field at any point, any random point in the middle, we can draw a Gaussian surface, a cylindrical Gaussian surface. This is from the side, so it looks like a rectangle, but it's actually a cylinder that has that point on its top surface, and it cuts into the plate on the bottom. So then, with this surface drawn, we write out our Gauss's law, equals Q enclosed, over epsilon naught O. I guess since I said these are infinite plates, once again, we can't use Q. In this case, it's going to be sigma for surface charge density, plus sigma, that's not a sigma, this is a sigma, sigma and minus sigma. So with our Gauss's law written, now we have to think about what's happening on all the different parts of this Gaussian surface. So I'm going to draw it a little bit bigger over here. This is our cylindrical surface. So this bottom part of it is actually like within, I don't want to draw this. Here, I'll draw a little like cross section here. And then that is where the plane is. The plane of the plate of the capacitor, that is. Alright. That's not quite how I wanted that drawing to go. Whatever. I'll just draw it like this. So you know there's minus charges in there. So what is happening on all the faces of this Gaussian surface? Well, on this bottom face, we're in the middle of a conductor, so that contributes nothing. These side faces, the round face rather, we know that can contribute nothing because we're in the middle of an infinite plate. It doesn't make sense for the E field to be pointing this way or that way because we're just in the center of an infinite plate. It's symmetrical. So the only face that actually contributes anything is this top round face here. So with that, we can simplify away the dot product and pull out the E, since we know the E field should also be pointing directly up or down, which is perpendicular, or rather parallel to our dA. So we get E integral dA is equal to Q enclosed. We can write that in now. The Q enclosed, so I guess first of all we have to define the radius of our cylinder to be R. So the radius is, or rather the Q enclosed is just pi r squared times the surface charge density. I guess in this case it's actually negative sigma. So now we can just expand out this integral. So what is the surface area that matters? It's just this top face of the cylinder. which is pi r squared. So pi r squared E is equal to pi r squared negative pi r squared sigma over epsilon naught. These cancel out, and you find that E is equal to sigma over epsilon naught. In this case, a negative sign because I chose the negatively charged side of the plate. But, I mean, in a capacitor, you know the E field is, of course, pointing from the positive side to the negative side. You just want to know what is the strength. So I'll just drop off the negative sign. It's sigma over epsilon naught. And there you have it. So with that, I think you should be pretty well prepared to apply Gauss's law in just about any scenario. So hopefully this helps you on your AP exam.